Hello people, Zach here again, in the darkness as usual, and this is going to be a follow-up to a previous video I made about how space-time curvature isn't real. Now that video kind of went into some inconsistencies in the mainstream theory. Like, one of the things was that space can expand faster than the speed of light, yet gravitational waves have to somehow propagate at the speed of light, or no faster than that, which didn't make any sense to me. That, and I kind of went into an explanation of what the speed of light actually is, which is rate of induction, and showed how if you assert a certain speed, that you have to consider the topology of the space that you're traveling through to account for the changes in difference. So like I said, if you're interested, you can go ahead and watch that, but this video is going to be entering into a different topic. And so the first part for this video is going to be about the geometry of space. So like I said before, space-time doesn't curve, and it also doesn't expand. And the reason for this is that space is the distance across, between, and beyond things. It is not a thing itself. It has no area, and it has no volume, because to have an area or a volume, you have to have a boundary that separates the inside of the thing from the outside of the thing. And space has no boundaries unto itself. It can only be bounded by things. So if there are no things and you're just talking about space itself, there's no boundary, therefore no area, no volume. If there's no area or volume, then it can't expand. But, and as a matter of fact, space, not only does it not have area or volume, but it doesn't have properties at all. Because to have properties is, to have a property is literally to own something. It's like it's something you have. But to have something, there has to be substance there, and space has no substance. I mean, you can give attributes to it, but it doesn't have any substance. And even if it did have properties, like if it had any properties at all, any properties it would have to be applied to the entirety of space. They couldn't be localized because space doesn't have any parts. I mean, that you can't like separate one part of space from another without actually having things. So yeah, I mean, like I said, space is not a thing, it's the absence of things, it's emptiness itself. When the distance between any two things is finite, it means that they're in the same space, and when it's infinite, it means that they're not in the same space, like they're in separate universes. So it's like why I can't travel to Mordor's, because Mordor is an infinite distance away from me. It's a completely different space. But anyways, that should cover one of the main arguments against space-time curvature for this video. But the second part is going to be about the postulates of general relativity. So the main reason I made this video was watching this video made by Veritasium, and this is mainly just boredom watching, and it was supposed to be on Euclid elements, like the fourth or fifth postulate. I think it was the fifth postulate. Has to do with parallel lines and how that leads to like hyperbolic spaces and stuff, which is interesting, you know, stuff to have in the background. But Veritasium somehow veered off of this topic onto talking about the equivalence principle and stuff, and they brought up the two postulates of general relativity. And the very first one that was there had to do with like defining like inertial frames of reference in terms of an object in free fall. And like I'm shaking my head, because there's no such thing as a real inertial frame of reference. And by real, what I mean is objective and universal. And the reason why there is no real inertial frame of reference is that you are in motion relative to every single thing in the entire universe, with the exception of yourself and the things that are still relative to you. So you are always moving. But not only that, but you are accelerating relative to every single thing in the entire universe, with the exception of yourself and the things that appear still to you or appear to be moving in a straight line at a constant speed relative to you. And so if you're accelerating relative to darn near everything in the entire universe, how can you be in an inertial frame of reference? You can't. If you're, by definition of inertia itself is that an object is still or moving in a straight line at a constant speed. If you're accelerating, then you're not inertial. But the video that I was watching on Veritasium on the subject, they were talking about how like this astronaut who's in the ship appears from their perspective to be moving in a straight line to the ship, and the reason why is that they actually are moving through a straight line, and that it's actually the space that's curved. And I'm just like, I'm shaking my head here again, because it's... No, the reason why they're not falling to the floor of the ship is because the ship itself is falling. I'm not gonna... For them to fall to the floor of the ship, they would have to be falling faster than the ship itself. They're not making any sense. And here's the thing, you know, if you can completely escape Earth's gravitational well and see like you're way out in the middle of deep space where you're not experiencing Earth's gravity at all, you would still be experiencing gravity, but you're not going to gravitate towards the walls of the ship, because for that they would have... What you're gravitating towards is not the object, it is the barycenter of a system of masses. And so because you're inside of a capsule, you're experiencing forces everywhere on the coming from every direction inside this capsule that's pulling you towards every side. And of course gravity is really weak, so it's going to take you a while to actually get towards the barycenter. But my main point here is that the barycenter of this system is not going to be on a wall. It's going to be in the air somewhere in the middle of the ship. So what you're falling towards is not a wall. You're falling towards somewhere in the middle of the ship, which to you makes it seem like you're weightless. I mean, think about it this way. Imagine if the entire Earth was hollow. Like, think like a Dyson sphere, but still had the same mass. Like, imagine if all of the mass on the Earth was on the outer side, and somehow you were inside the Earth. Where would you gravitate towards? Well, it depends, because you're being pulled in every single direction, but you're being pulled by an equal amount. So, like... Yeah, it just depends on where the barycenter is at. But, yeah. So, those are my thoughts on that. Like I said, there's no space-time curvature. It's not real. It's imaginary. It's like a streamline in a vector field, or like a flux line for like a magnetic flux, or like a contour on a topological map. It's what happens when you look at something from a different perspective. Now, that perspective can be useful, especially for mathematical purposes, but the reality is that it's not real. And I think people who are mathematicians who pretend to be physicists don't think of it this way, because they think that math is real. Like, they think that God created the universe in the language of math. And they don't realize that the universe wasn't created based on math. Math is a description of the universe. It's completely backwards. Everyone looks at everything backwards and upside down. But, oh well. Thanks for watching.